All right, we've looked at discrete random variables, so discrete being something that is countable. And now we're going to start looking at continuous random variables. So it's any value on the real number line. So there's no real limit to the accuracy that can be measured, which is good, but it makes stuff a little bit more difficult. A function whose graph models the histogram, so something like this. We did calculate these rectangles by hand, the area. We're now looking at actually putting a function to this. This function is called a probability density function, and there's a few criteria for that probability density function. We'll go over that in a second. The thing to note though is that if we are after actually calculating a probability using this probability density function or PDF, then you're actually after the area underneath that graph. So if you want the probability between 82.5 and 83.5, then you can actually just use this integral between 82.5 and 83.5 of the function, and then that would actually give you the correct probability between those two ends of, let's say. So probability density functions. For something to be classified as a probability density function, then there is a set of, I suppose, conditions. So you can restrict the domain. In fact, in some cases, you have to restrict the domain. Okay, so for a probability, it can't be negative, right? You can't have a negative probability, so the area can't be below the x-axis, which means that your entire function within the restricted domain has to be positive. So everything has to be above the x-axis. The area underneath the graph has to equal 1. So between the smallest and the largest, i.e. A and B in this case, that area has to equal 1. Just like probabilities, the sum of probabilities has to equal 1. This is that exact same condition. So a PDF, the area from the smallest to the largest part of the domain must equal 1, which is what all of these dot points basically say. So that to be defined, condition-wise, it has to be all positive, and then it also has to equal 1 when you sum it together. Alrighty, examples. So example 1, consider the function f with the rule, it's a hybrid function, so we've got more than one part of it. The important part of this is that what it's saying is that between 0 and 1 is our probability density function. Anything outside of those two values, the function is then 0. So it's actually not calculating an area underneath that. So it's this portion here, between 0 and 1, that's actually going to create our probability function. So the first part of this is to sketch the graph. So my method for sketching, I'm just going to chuck it into the calculator, but you should be recognizing this as an upside down quadratic with y-intercept of 1.5 and an x-intercept of, I believe, 1. You can put this into your graph, change your domains, or your scale so you can actually see it decently. And then I'm just going to sketch it. So 1.5 and 1. I'm asked to then show that this is a probability density function, so don't just assume that it is. It's asking us to show that it is. I have seen this in past exams, so be aware of that. To show that it's a probability density function, you have to meet the two criteria. So the entire function within the domain has to be positive. So f of x must be greater than or equal to 0. And then obviously looking at this graph, we can see that it is. The other thing is that the area between that restriction of 0 to 1, the area has to be equal to 1. So doing the integral between 0 to 1 for that function, so we'll have the integral is 1.5x minus 1.5x to the cubed divided by 3, and then substituting in everything, we get out that that area is equal to 1, which by definition then means that this is a probability density function. So that is shown in that question. And then part C is asking us to find the probability of x being greater than 0.5. So for x to be greater than 0.5, you're looking at an integral between 0.5 and the maximum, which is 1. So substituting in those two values, we can find out that area. Interesting little side note here is that with an integral or a top restriction of 1, then that's going the entire graph, and because it's a probability density function, the area underneath the entire graph should be 1. So this portion should always come out as 1 because I'm looking at it at the top restriction. So be aware of that, I suppose just as a shortcut. And then the second part is what we're removing off. So you put that into your calculator, and either way you'd get out this result of 0.3125. And then that's your probability of being greater than 0.5. Second example, we've got the time in seconds it takes for a student to complete a puzzle is a random variable x with a density function given by this. We're asked to find the probability that a student takes less than 12 seconds to complete the puzzle. The actual function says that you're dealing with something where the probability density function is all values greater than 5. So if you want something less than 12, then what we're actually looking at doing for this particular question is an integral between 5 and 12, because 5's the minimum for that function. And then that's of that 5 on x squared. And then when we integrate that, we'll get negative 5 on x. And then substituting in gives us a result of 7 on 12. So the probability of x being less than 12 is 7 on 12. The second part of this is a given that portion. So we're asked to find the probability that a student takes between 8 and 10 seconds, given that he takes less than 12 seconds. So between 8 and 10 seconds, given that less than 12. Noticing that this second portion, 8x less than 12, is actually what we just did in part A, so that's going to make life a little bit easier later on. So it's a given that the top is the intersection of the two, so the only place that x is between 8 and 10 is between 8 and 10, so this 12 part actually doesn't affect what's on the top, so the intersection of these two is just this. The bottom, the denominator, is just the probability of x being less than 12, which is what we've just calculated above. We will have to calculate the probability of x being between 8 and 10. So that's the integral with a lower bound of 8 and an upper bound of 10 of 5 on x squared dx. And then when we go through and we do this, we'll get out a result of 1/8. So going back to that original probability, we know that our probability of x being less than 12 is 7/12. So now actually just substituting this in, we get 1/8 divided by 7/12, which is 3/14 as a solution.